welcome back. Let's continue our look-see at the Proxxon FF230 Fine Milling Machine 230. In previous episodes, we looked at the table as well as the Z-axis. In this episode, we are going to turn our attention to the spindle as well as the power head. Now, much like earlier videos, I'm going to divide this into three different parts. The first part will just be a grand overview and operating principles. In the second part, I'm going to tear it down and we'll see what sort of maintenance notes we can take. And then in the third part of this video, after it's back together, we're going to run some tests. A test indicator here, a ground rod, and we'll get a handle on a runout of this machine. A tachometer, and we'll see how fast this thing is able to spin your tool. Let's start off with the business end. Here is the collet, and your bit is going to fit into there, and then you tighten this nut down on your bit. Proxxon has included these stamped steel wrenches, one that is going to hold on to the spindle, and the other one that's going to let you tighten on the collet nut. Very straightforward. What's not entirely straightforward is sometimes your tool, your bit just doesn't really want to get in there well. And if that's the case, well, you just have to back off the collet all the way. And usually then you can get it in like that. Well, now that we have it apart, let's take a look at this how this collet works. Its configuration is rather similar to an ER series collet. It's not an ER series, however. It's proprietary, very, very annoying. Basically, the collet is fit inside the collet nut with a little retaining ring that is eccentric, which basically means you can wiggle it out. That happened a little too easily. Sometimes it's stuck. There we go. So it wiggles out, and basically you got an eccentric shelf there, and that shelf is going to grab onto the groove of the collet, and what that's going to allow is ejecting your bit when you loosen the collet nut. Maybe I'll demonstrate that in a moment. Yeah, so that's just how it works. It's this collet is going to hold onto the tool, and when it is jammed into the spindle, which is tapered, the spindle is going to impinge down on these, I don't know what you call those parts of the collet, and squish the collet onto the bit. Hold it good and tight. Yeah, these are proprietary, and Proxxon only includes 3 of them in the mill. In the mill package, you got a 10mm, you got an 8mm, and a 6mm, and you have to purchase these ones separately. That gives you, that's a 5, a 4, a 3, and then we got 2 odd ones here, which are imperial. You got a 1/8 and a 3/32. What's very annoying is that these are proprietary, and Proxxon doesn't have any imperial other sizes. For instance, there really should be a 3/8, which the 10 and the 8 is, it doesn't work. You can't use a 3/8 bit with this machine. Anyways, that's a little bit annoying that you have to buy these separately. Well, here's a 10mm one. That's the one that I find I'm using the most often. Plop it in there like so. Wiggle it up. And put our bit in. And we can tighten it to hand tightness like so. Then the bit won't fall out. Grab onto the spindle. And there you go. And that should do it. Now to eject the spindle, it's the opposite procedure, but what you'll notice is that when you loosen it, the bit's actually still held in really quite tightly. What you got to do is you spin the collet nut down a little bit further, and you give it a second little quarter turn, and that's where that shelf interfaces with the groove that releases the bit from the collet. Yeah, so that's not bad. You get a range of sizes in metric and a couple imperial ones. You can extend your possibilities by using a drill chuck, but this is really not nearly the same as actually sticking your tool straight into the collet. First of all, these drill chucks, they don't have the best concentricity. directly in the collet, we're going to get the lowest amount of runout. And then on top of that, we're going to be increasing the Z height when we're using a drill chuck. This drill chuck, it's not included with the Proxxon Mill package. You got to buy this separately, and it's not some standard part that you can just buy on the internet. The shaft is special. It's a Morse taper that just fits into the drill chuck, and then it has a straight 10mm shank on this end that allows you to stick it into and hold it on with that collet. Necessary, you absolutely need one of these, but you're not going to use it for milling, only really for drilling and maybe a few other types of tools that are nothing too consequential if it's not perfectly concentric. And onto the power head, you got on and you got off there. I really do appreciate how Proxxon put the electronics box in this location, as opposed to putting in some sort of wart here on the back of the motor. This switch is really nice and conveniently located. Now to change speeds, you undo this locking knob here and you can swing over the cover, and you got pulleys. You got 6 different pulley speed ratio options, and you can change the ratio by sticking in a 5mm hex key there. This lever adjusts tension. You loosen up the tension, and now you can switch off to a different speed. And here I just lowered it down a little bit. Get that belt on nice and properly. And there we go, different speed. Now the speeds we're going to check out later on in the video, but there is a decal here which is very, very shiny, and trust me, it's about as difficult to read in person as it is here in the video. So you got the 6 different speeds. Proxxon does say in the manual that for how much pressure you are supposed to put on this pulley tension is not very much. I do find that it's you can more or less hear with your ears as to what sort of tension is right. When it's working proper, it sounds nice. It sounds good. If you hear it squealing or you hear it making some sort of a rubbing noise or something like that, either the pulley is not on track properly, this shaft needs oiling, I'll show that a little bit later, or the tension is not right. It's either too tight or it's too loose. And now on to the teardown. Before we actually get into it, let's just take an outward look at the materials. This pulley cover is made out of plastic, probably ABS. The majority of this power head housing is prefabulated aluminite. However, there is some steel involved. For instance, this idler pulley support plate is steel, as well as is the motor plate. The motor can is steel, and it'd have to be steel for the magnetic purposes. The end caps of the motor are, well, once again, prefabulated aluminite. Now let's remove the idler pulley. Proxxon recommends oiling this location every now and then. Let's completely remove that screw and see what sort of wear surfaces are present. Okay, that screw pulls out, got a washer on it, and we can see immediately a steel shaft and a bronze bushing. So remove that pulley, and we can lift this belt, lift this pulley off, and let's take a look at that up close. Get it in focus. Okay, so that's the steel shaft that the pulley is sitting on. So it's going to need a little bit of oil there, and hopefully over time the oil will wick its way down the shaft by gravity as well, and will lubricate the bottom. Internally, they are 2 bronze bushings. So You might actually want to oil the bottom of this separately. I actually did find that to be the case once. It was making an odd noise, and I kept oiling the top, and it didn't fix the noise, but I oiled the bottom, and well, then it started running a little bit more smoothly. So Proxxon's advice might need to be extended a little bit. Now let's take a look at how pulley tension is achieved. Well, this lever is going to pull this slider back and forth. Interesting little plastic window right there. Let's take that pulley plate off. Need a 4mm hex key. Okay, now the pulley support plate can come off. And here is the piece that the pulley column is going to interface with. And we got a piece of plastic here, which is falling apart. So that's the window into the electronics box. This electronics box, nothing special in here. It's a full wave rectifier. It's going to be giving DC voltage to the motor. Once again, I do like that the electronics box is in this location and the on-off is right there. Let's remove the motor support plate. This is the first of 3 4mm cap screws that hold the plate onto the housing. And notice that there's a washer in that location, bit of an odd location. Make sure that you don't lose those, 3 of them in total. And now we can carefully tilt this motor back, being careful to not lose these pesky little washers. And we can see, lost. And we can see how this motor pulley can be adjusted for tension independently of the spindle pulley. You can see some nuts there, you can see an arc, and then the motor can be shifted, adjusting the location of this pulley. This pulley is made out of wood, which is unusual compared to the rest of the pulleys made out of aluminum. Now, I figured the reason why it's made up of this material and not that is because aluminum transfers heat and wood doesn't transfer heat. And in my experience, this motor can heat up really, really, really hot. Now here's a spindle pulley. There is a set screw there that I have this hex key in. I've undid it. However, the pulley, it is press fit onto the spindle. I would have liked to have taken it off for this video, but I'm not going to bother doing that. Let's get on to some tests. But before the tests, one more thing to check out, and that is to take off the motor can and see the motor inside. Here's the end cap. A rather nicely machined hunk of aluminum. And I'm going to pull the motor can off. Oh, magnet's got it stuck on good. And there we go. It has lots and lots of windings, and that's going to provide lots of torque at low speeds. And we got some good-sized brushes. They look replaceable. And I see a shitload of carbon splattered all over the place. That should really be cleaned off every now and then, otherwise it might cause trouble. Nameplate power consumption is 140 watts. I got it hooked up to the kilowatt here, and let's just see how much power this mill draws when it's not doing any actual work. And it ends up being quite a bit less than 140 watts. Ends up being maybe 46, 47 watts. That said, I do sometimes run this mill hooked up to the kilowatt so I can see what is going on. And with heavy milling in steel, I have seen it go up to 150 watts. I do that. I monitor it to make sure that I don't keep it at that power consumption for very long because the machine heats up really quickly. Nameplate RPM is 4,000 revolutions per minute. I placed a reflective sticker on the motor pulley, that way we can check out the no-load RPM. And I measure 3,800 and getting close to 60 RPM. Close to nominal, not quite, but close. But what's of greatest interest is the speed of the spindle. I got a sticker here stuck on an end mill. I have the top pulley in low gear and the bottom pulley is in speed level number 1. That's coming out a little bit faster than the 280 nominal RPM. Well, 322. Okay, that's gear level number 2. And we're getting about 909 RPM as opposed to 870. Now speed level 3. And it's coming out to almost 1300 RPM, 1264 maybe. Now let's drop that back down to speed number 1 and put the top pulley into high gear. 595 as opposed to 560 RPM. Speed number 2 in high gear. 1660 some odd as opposed to 1500 nameplate. And lastly, speed 3 on high gear. That is the fastest that this machine will run. And we're coming out with 2300, a little more than 2300 RPM as opposed to the nameplate being 2200 RPM. That is the maximum speed that this mill will operate, which calls into question using the smaller bits that you might be able to use with the smaller collets. Small bits, you really want higher speeds than that. While RPM is interesting, what is much more critical is the spindle concentric. What's the runout of this machine? I have a 100th of a millimeter test indicator that is indicating off of the inside of the taper in the spindle. And let's put it through 1 revolution and see what the runout is. Okay, it's about a quarter of a revolution there. There's a half a revolution. 3/4. That's about a full revolution. What we see is runout's quite low. The intrinsic runout of the spindle, it's well under 100th of a millimeter. Yeah, it's pretty good. Now, how does that translate into runout of a mounted bit? I have a 10 millimeter ground rod installed, chucked nice and tight, and let's see what the runout is now for 1 revolution. Well, for 1 revolution, that was about 5/100ths of a millimeter. A lot poorer than the intrinsic runout of the spindle. And now runout at a more typical working distance, end of an end mill would be about 30 millimeters of extension from the collet. Yikes. Runout increased a lot. So let's try a smaller collet and a smaller end mill. Here's a 3 millimeter end mill. It's installed about 1.5 centimeters up into the collet. Measuring close to the collet, we get not a huge improvement. About 2.5/100ths of a millimeter of runout. Now let's measure runout 20 millimeters away from the collet end. That would be a typical amount of bit extension that you'd use with a 3 millimeter end mill. Let's do 1 revolution. And what we find is that runout is increased considerably. It's now at about 5/100ths of a millimeter. What that means is that this collet is suffering from a type of runout. You got two types of runout. You got radial runout, which is when the axis of rotation is not dead center. That's not the problem here. The problem here is axial runout. And axial runout, well, that is when the axis is at an angle. I'm exaggerating here. But basically what that means is the further you go from the business end, the worse the runout is going to become. Now, just for shits and giggles, let's take a look at runout of the 10mm ground rod installed in the drill chuck that is now put into the 10mm collet. We are looking at over 11 centimeters of extension from the collet and about 6 or 7 centimeters from the drill chuck end. And let's see what the runout is. That's not as bad as I thought it would be. It's about a 0.2 of a millimeter, 20/100ths of a millimeter. I do believe that these collets are the weak link in this milling machine. They're proprietary, meaning you got to get replacements from Proxxon, and they have limited sizes available. And not only that, I think that their design is a bit flaky. They are way too short for this style of collet that clamps down on the shank only at the front end. What that means is that when your shaft is clamped into the collet, there's still going to be a small amount of wiggle room at the rear end of the collet, and I do believe that is at least one of the sources of axial runout that we measured just a moment ago. Not only that, but also for this collet to be jammable up into the taper, well, the rear end is going to have to be very slightly undersized. And that's going to give another point at which there can be a little bit of wiggling and a little bit of axial runout added. I have no idea why Proxxon decided to go with this proprietary collet system. Why didn't they just go with that ER series collet? They're way, way better. An ER series collet, in contrast, when it clamps down onto your shank, it clamps down from one end to the other end nice and evenly, and they're available in like really high specifications, high concentricity, low runout. Yeah, I wish that they went with those instead. ER series, their included angle is 16 degrees, and to the best that I can measure, these collets from Proxxon, they appear to be about 8 degrees included angle. In case you know if this is some sort of specification that I don't know about, and maybe it is something standard, deprecated or uncommon, let us know in the comments below. But I kind of doubt it. I think it's proprietary. And so that concludes our 3-part look-see at the Proxxon fine milling machine FF230. Except I think we need a 4th part. How about all the accessories that are available? I think I got them all. Well, a future video. Thanks for watching. Subscribe. I'll see you next time. Bye-bye.